Welcome back. This will be a video lecture on section 1.2, length and angle, the dot product. I've broken this section up into 6 subsections: the dot product, length, distance, angle, orthogonality, and projections. I'm going to cover these first 3 topics in this video lecture, and I will save angle, orthogonality, and projections for a second video lecture. So let's begin with the dot product. The dot product takes 2 vectors of the same length and it returns a single number. And this number is what's going to allow us to talk about the angle between these vectors. So it allows us to bring geometry into our study of these Euclidean spaces. So let's take a look at the definition of the dot product in some detail. All right, so given 2 vectors u and v, with components u1 through un and v1 through vn. So these are 2 vectors in a common Euclidean space. The dot product of u and v is defined as follows. Well, first let's understand the notation. So we take the 2 vectors, u and v, and we put a simple dot between them. So that's our notation for the dot product. So this is alerting us to the fact that we're computing what's called the dot product. Now, what do? I always think of this calculation as composed of 2 parts. In the first part of the calculation, I grab, let's say, the first component of u and the first component of v, and I form their product. And then I do the same with the second components of u and v. And I continue this process until I've exhausted all of the components of u and v. So the first step in computing a dot product is just to get the components, the products of the components, u1 and v1, u2 and v2, on out to un and vn. Having formed all those products, the second part of the calculation is to add up the sum. So compute the sum of those products, if you will. So that is called the dot product of u and v. Now what's important to remember here is that we start with a pair of vectors on the left, and after we're done computing the dot product, we have a single number or a scalar here on this right-hand side. That right-hand side is just going to be a single number. Now, I think it will help us gain some appreciation for the dot product if we work a few examples. So, in each case, when permissible, compute the dot product of u and v. So, let's head over to the document camera and work these out in detail. All right, welcome back to the document camera. Let's work out the details for 1, 2, and 3 in this problem, and let's remind ourselves what we're doing. In each case, when permissible, compute the dot product of u and v. So let's take a look at problem 1. So we see in problem 1 here, u is a vector in R3, v is another vector in R3. That's compatible. And the dot product is going to be what? What I get when I do component-wise multiplication. So I'm going to have the 1 times the negative 2. I'm going to have the 0 times a 1. And a negative 1 times the 3. And I'm going to add these pieces together. So you do component-wise multiplication and then addition. Now, what do we get? We get negative 2, 0, and negative 3. And so that's going to result in negative 5. So that's the dot product of u and v in this first case. Let's take a look at problem 2. I've got u as a vector in R2 and v is a vector in R3, and so this is not compatible, right? So there is no dot product. So u dot v makes no sense. Right? They have to come from the same space, same length. Okay, finally, part 3. I've got a vector in R4. I've got another vector in R4, so the dot product makes sense. And again, I do component-wise multiplication. So 2 times 0, the 0 times negative 3. I'm going to have the negative 1 times 1, and the 4 times the 2. And then I add these pieces together. So I get 0, 0, negative 1, and 8. And so the result is going to be 7. So that's how we do dot products. Fairly straightforward. The only thing you have to make sure you understand is that the compatibility is necessary, right? We have an R2 against an R3 vector here, and that will not make sense. That's not compatible. So we have legitimate products in cases 1 and 3, and something that is not compatible in case 2. All right. Hopefully that gives you some insight into how to compute the dot product, and I'll meet you back at the class notes so we can continue. Now, Theorem 1.2 contains 4 essential properties of the dot product. So let's look at each of these 4 properties. I will prove 2 of them for you at the document camera, and I will leave 2 for you to do on your own. Now, in order to get going here, let's let U, V, and W be vectors in some common n-dimensional Euclidean space, and let's let C be some scalar quantity. All right, property A, the dot product is commutative, and what that means is it doesn't matter if I form the dot product in the order U dot V or V dot U, either way I'm going to get the same result. So we say that the dot product is commutative. Now property B says that the dot product distributes over vector addition. Let's take a look at this in some detail. So suppose we want to calculate a dot product of the form U dot a sum V plus W. So U is being dotted with a vector sum. What this theorem tells us is that we can take the dot product over this vector addition. In other words, we can take U dot V plus U dot W. So on the right-hand side here, we'll see U dot V plus U dot W. So in short, the dot product distributes over vector addition. Now, I will caution you, when you're reading this, you really should understand that this plus sign is doing different things on each side of this equation. So on this side, on the right, this is the sum of 2 real numbers, and so this is just ordinary arithmetic. This is just the sum of some real numbers. On this side, that plus sign is standing for vector addition. So this is a little more subtle than it might appear at first, but nonetheless, it's a law that we have available to us. It's a very important law, a very important property of the dot product, that it distributes over vector addition. Now, property C is a kind of associative law. Let's take a look at this. On this left-hand side, we've got a vector C times U being dotted with a vector V. And on the right-hand side, what do we see? We see the dot product of U and V first, and then the multiplication by the factor or the scalar C. And so essentially what we're allowed to do is pick up the parentheses and reassociate them, and we'll get the same thing no matter what. So either we scale first and then take the dot product, or we take the dot product first and scale second. Now let's take a look at property D in some detail. Property D is saying something interesting. It says, anytime I take the dot product of a vector with itself, I'm going to get something that's bigger than or equal to 0. And it strengthens this result. It says, if the dot product of a vector with itself is ever equal to 0, that can only happen if and only if the vector itself is the 0 vector. Now, in case you haven't thought about if and only if statements for a while, what this is saying is that there are 2 implications that are being suggested here. It says, if the dot product of a vector with itself is equal to 0, then that must be the 0 vector. And it's also saying that if I start with a 0 vector, then the dot product of that vector with itself must be equal to 0. So there's 2 different implications that are being suggested here. Now, we're going to go to the document camera, right? And I'm going to work out parts B and D, or properties B and D, for you in some detail. We'll comment on A and C a little bit more, but I really want to emphasize the proofs of B and D, and then I will ask you to think about how you would prove A and C in light of those proofs. All right, so join me over at the document camera for the proofs of these parts B and D. All right, so welcome back to the document camera. We're going to work out 2 of these 4 properties from Theorem 1.2. We'll work out the details for B, and we'll work out the details for D, and then I'll leave you to think about how you could imitate these results and get proofs for A and C. So I'll leave those for you to ponder. So let's start with B, and I'm not going to have enough room on this sheet to work these out, so I'm going to go to a separate sheet, but let's remember the first thing we're going to work out is this distributive law for the dot product over vector addition. Now, in doing this, I'm going to need to get some components for u and v and w. So let's just set up some notation here. Our vector u is going to have components u1, u2 up through un. V will have these components. And w will have these components. Now, remember what I'm trying to prove. I'm trying to show that when I take the dot product of u with the vector sum v plus w, that's the same thing as distributing this dot product across this vector sum. So u dot v plus u dot w. Now, what I'm going to do is I'm going to start here on the left-hand side, and I'm going to do the vector sum, bring in the dot product, and I'll show you that by a process of manipulations that we can end up with this right-hand side. Okay, so let's begin with the vector sum. When I do v plus w, I'm going to get component-wise addition. So I'm going to have something that looks like this. Okay, so that's just v plus w. And now I want to bring in the dot product of that vector with u. Now what's that going to do? We know that when we take a dot product, we're going to get the product of the first components, the product of the second components, the product of the nth components, and then those products are added together. So we're going to get something that looks like this. u1 is going to multiply v1 plus w1. u2 is going to multiply v2 plus w2. This is going to continue. And our last product will be un times vn plus wn. Now you can probably see where this is going, right? The next step is going to be to use the distributive law on each and every one of these products. And so we can take this, for instance, this first product can be written as u1v1 plus u1w1. Then we'll have u2v2, u2w2. And this continues until we get to un, vn, un, wn. All right. Now I'm going to take all of the u and v products and commute them over to the left, and I'll take all the u and w products and commute them over to the right. So I can kind of just change the order in which I'm doing the addition here. And for instance, I'll first grab u1, v1, u2, v2. There will be a u3, v3. I'll grab that one, and the un, vn, and I'll pull all of them here to the left. Then I'll take all the pieces that remain, all the UW products, and I'll push them to the right here and associate them. And now we just have to step back and look at what we've got here, right? We've got products of first components, products of second components, products of nth components added together. And this involves the components of u and v. And so we recognize this as u dot v. And then we do the same thing here, right? We see that products of u, first components of u and w, second components of u and w, nth components of u and w. So we recognize that as u dot w. Okay, so we can see just by starting with that left-hand side and just carefully working our way through and using the normal rules of arithmetic along the way that we can work out u dot v plus w is u dot v, right? That u dot v and u dot w. All right, so that's that distributive law. Now, one thing I want to point out, though, is that this distributive law, although we normally write it this way, right, where u, the vector that's by itself, is on the left here, and it's dotted with a vector that's on the right, the sum on the right, it works the other way too. So if we had v plus w dotted with u in this order, right, it's also equivalent to v dot u, w dot u. In other words, that distributive law would work whether this vector sum is on the right or on the left, okay? And that's really just a product, that's an artifact of the commutative law. So because the law vector dot product is commutative, I could take this dot product, I could flip the order of the dot product, use the distributive law that we've just worked out, and get this result here. So in other words, the distributive law is more widely applicable than it would look just from the statement of theorem 1.2b that we stated. It's actually, the distributive law works on both sides because of that commutative law. Okay, now let's work out part D. We want to show that the dot product of a vector with itself is always bigger than or equal to 0. And then we want to show that the dot product is equal to 0 if and only if the underlying vector is the 0 vector. All right, let's prove part D, and let's start with a fresh sheet of paper here. Give ourselves some room to think. So for part D, there's a couple of things we have to show. First, we want to show that the dot product of a vector with itself is always bigger than or equal to 0. Now, this is fairly easy to do. Let's just give ourselves a vector u with components u1, u2 on out. And let's imagine if I take the dot product of u with itself, I'm going to basically have u1 times u1, u2 times u2, and this is going to go on out to un times un. So I form all those kind of component-wise products, and then I add them together. That's the dot product of u with itself. And then we can easily recognize that this is just u1 squared. That's u2 squared. And this continues until we get un squared. And we can see very easily that this is a square, so we know that this term is bigger than or equal to 0. This term is always bigger than or equal to 0. And this term is always bigger than or equal to 0. So in other words, this is just a sum of terms, all of which are bigger than or equal to 0. So the cumulative effect is that this will be a term that's bigger than or equal to 0. Okay? So let's take one thing away from this, though, right? That in addition to showing that u dot u is bigger than or equal to 0, we also know that u dot u is the sum of the squares of the components. Okay? That's a very useful idea. So one thing we want to highlight is that u dot u is equal to the sum of the squares of the components. Very, very useful. Now, what is the rest of part D? We want to show that u dot u is equal to 0 if and only if u is equal to the 0 vector. And this double arrow, this is just shorthand saying I have to show that if this is true, then that implies this. And the backwards implication is that if this is true, that implies this. Now the harder half is this direction. Let's assume that this is true. Okay, let's assume that u dot u is equal to 0. Now one thing we know is that u dot u is the sum of the squares of the components. So therefore, u1 squared plus u2 squared and out to un squared is equal to 0. But now remember, each one of these is a number that's bigger than or equal to 0. So in order for this sum to equal 0, each one of these terms must itself be equal to 0. So I'm claiming that this forces the conclusion that each and every one of these pieces is equal to 0. In other words, if any one of them were positive, the entire sum would be positive. So the fact that this sum of squares is equal to 0 means that each one of the parts is itself equal to 0. But if u1 squared is equal to 0, that means u1 is equal to 0. And if u2 squared is equal to 0, u2 has to equal 0. And finally, if un squared is equal to 0, un must equal 0. And what does it mean? That means that the vector u consists of components that are entirely 0, right? It's 0, 0, 0. And that's exactly what we mean by the 0 vector. Okay, so we've shown this direction. U dot u equals 0 implies u equals 0. The other direction is actually quite a bit simpler. Let's assume that u is equal to the 0 vector. Now, what does that mean? That means that the vector u consists entirely of 0 components. Then what? If all of the components are 0, then u dot u is just going to be 0 times 0 plus 0 times 0 plus 0 times 0. So when I do the component-wise multiplications, I'm just going to get products of zeros. And each of these products is 0, and the sum of zeros is 0. So this is just equal to 0. So we've shown this implication. If u is equal to 0, that implies that u dot u is equal to 0. So these are not these two directions are not equally difficult. This is the one that's got some subtlety to it. If u dot u is equal to 0, that implies that u is the 0 vector. This direction is actually fairly straightforward. If u is the 0 vector, then the dot product of u dot u is equal to 0 is fairly straightforward. So I want to work a problem for you that I'm calling FOIL for dot products. Now, you probably remember the acronym FOIL from when you learned how to multiply two binomials, F first, outer, inner, last. And what I'm claiming in this problem is that there's a version of FOIL for dot products. So here's the setup. So let u and v be vectors, and let a, b, c, and d be some real numbers, some scalars. Now, on the left-hand side, we have to imagine we've got some expression like this. We've got AU plus BV forming some vector, and we've got CU plus DV forming another vector, and we're taking the dot product of those two vectors. Now, what I want you to do is just kind of step back and just kind of think of this as a binomial, like maybe AX plus BY times another binomial CX plus DY. If you think about it that way, then you can imagine how the FOIL operation is going to look. I'm going to take AU dotted with CU, AU dotted with DV, BV dotted with CU, and BV dotted with DV. Now what I'll show you, and we'll do this together over at the document camera, is that we can take that and we can reduce it down to what we're seeing here on the right-hand side. The main idea here, though, is that we can kind of carry out this dot product operation just as we would ordinarily multiply a pair of binomials. So join me at the document camera and I will show you how we can turn this left-hand side into the right-hand side. All right, welcome back to the document camera. We're going to work out the details for our kind of FOIL dot product. And let's just remember what the left-hand side looks like. We have a linear combination of u and v with scalars a and b being dotted with another linear combination of u and v, this time with scalars c and d. Now what I'm going to do, and this is just to kind of keep things cleaner initially, I'm going to collapse this linear combination into a single vector that I'm going to call w. This just keeps things a little cleaner at the beginning here. Now, I can use my distributive law here and write this as w dotted with cu plus w dotted with dv. And then I can use my associative law. I can pick up these parentheses and reassociate these things and do the dot products of the vectors first and the scalars next. And so this will look like C w dot u and d w dot v. And this is where I'm going to have to stop the main part of the calculation here. I'm going to have to go off and I'm going to do a couple of side calculations because I'm going to simplify this and I'm going to simplify this. Well, they're actually not going to look simpler, but I'm going to find ways to reimagine w times u and w times v, and then I can insert them into this and finish the argument. So join me over here. Let's just do some side calculations. Okay, so I want to think about what w dot u would look like. So here, remember, here's w. So I'm going to have AU plus BV dotted with U. And I'm going to get, when I distribute this, I'm going to get AU dotted with U and BV dotted with U. That's going to be equal. And again, I can use this associative law to pull up these parentheses and reassociate them. And I can write this one as A u dot u and B v dot u. Now I know that in the end, I'm going to want my expressions to consist of only u dot u's, v dot v's, and u dot v's. So I'm going to use the commutative law here. I'm just going to do one extra step. This is just to help me get to my final form. I'll use the commutative law and write this one as u dot v. Okay? So that's one of my side calculations. I'm going to be able to use that to replace that one. And I'm going to do now another calculation for w dot v. So there's w, and now I'm going to dot it with v. And what's that equal to? By the distributive law, I'll be able to write this as au dot v, bv dot v. And again, by association, and this one's already in the form u dot v, so I'll leave it at that. Now what I want to do is bring these back up here into the main calculation and finish up the problem, right? So we're going to have, I'm going to start it over here just to give myself some space. So I'm going to take C, and in place of w dot u, I'm going to write this. And in place of w dot v, I'm going to write this. Okay? And now what I'm going to do is use the normal distributive law for arithmetic. Notice that now everything in sight here is just a real number. So I can use my normal laws of arithmetic, my distributive laws, and associative laws. I'm going to multiply through by c, and I'm going to write this as AC u dot u, CB, I'll write it as BC u dot v, AD u dot v, and BD v dot v. And we're almost home. The last thing I'm going to do is I'm going to notice that there's a common u dot v in these two middle terms. So I'll factor out the u dot v and I'll be left with BC plus AD. Now I can commute that. I'm going to write this as AD plus BC u dot v, and then finally BD v dot v. And this is exactly the final form that we're looking at. This is our FOIL operation. We can start here and end here. The main thing to remember though, and this is just justifying, this is just kind of showing you the necessary steps to justify a claim like this. The main thing though is that I can take an object like this, a pair of linear combinations, and I can literally work out the final result, break it down into calculations that just involve the dot products of the underlying vectors. Okay, so products of linear combinations can be broken down in this way. All right, let's head back to the class notes and continue. Our next subsection is entitled Length, and in this section we'll learn how to talk about and compute the length of a vector. And let's begin with something familiar, right? The distance formula. And let's begin with the distance formula in the plane. So let's say you wanted to compute the distance from the origin to a point P with coordinates A and B, and this is occurring in the two-dimensional plane. Well, we know from the distance formula that's simply going to be the square root of a squared plus b squared. And we can think of that, here's a picture up here for you, we can think of that as really just a utilization of the Pythagorean theorem. So if this point has coordinates a and b, and I've drawn it here in the first quadrant, that base here has length a, this leg here has length b, and the hypotenuse, which is what we're trying to compute, the length of this blue segment would be the square root of a squared plus b squared. So in the plane, we can see that the Pythagorean theorem gives us the justification for the formula, the square root of a squared plus b squared. Now, if you're very careful, you can lift that result out of the plane and into three-dimensional space, and you can easily show that the distance from the origin in R3 to a point with coordinates a, b, and c is given by the formula the square root of a squared plus b squared plus c squared. In other words, you just sum the squares of the coordinates and then you slap on a square root, and that gives you the distance from the origin to that point P with those coordinates. Now, in general, in Rn, if we want to compute the distance from the origin to a point with coordinates a1, a2 on out to an, it's the same basic rule, right? That distance is going to be the square root of the sum of the squares of the coordinates. So that's how we compute distance in each of these cases from the origin to a point in space with some specified coordinates. Now, the distance formula leads us naturally to our notion of length or norm for a vector. So the length or norm of the vector u with components u1 up through un in n-dimensional space is given by this formula here. Now let's talk a little bit about this left-hand side first. So when we have a vector u, we specify that we're computing its length by using double absolute value signs, right? So we've got two vertical bars on the left and the right, and that announces to us that we're computing the length of this vector. And what we essentially do is we take the tip of this vector, so the tip of the vector u is going to have coordinates u1 through un, and we simply compute the distance from the origin to that point with coordinates u1 through un. So this formula here, right, that the length of the vector is simply the square root of the sum of the squares of the components, is coming directly from the distance formula in Rn. This is simply the distance from the origin to the tip of the vector. And that gives us a very natural notion or natural idea for the length or the norm of a vector. Now, let's put this to use just to make sure we're understanding how this formula works, right? So if I specify a particular vector in R3, let's say u has coordinates or components, 3, 12, and -4. To compute the length of this vector, all we have to do is take the 3, the 12, and the -4, square them, add them together, and then take the square root. So we're simply going to take 3 squared plus 12 squared plus -4 squared. That's going to sum to 169. When we take the square root of that, we get 13. So this vector u has a length of 13, or we could say it has a norm of 13. Now I really want to show you an interesting connection between the dot product and the length of a vector. So let u be a vector in Rn, and let's say for the sake of argument that u has components u1, u2 up through un. Now what I want to do is do a calculation here. I want to form the dot product of the vector with itself. So I'm taking u dotted with u. And so I have to take the first components, which is u1, I have to take that product with itself. So I'm going to have u1 times u1, u2 times u2. on out to un times un. So I'm going to see all of those products laid out here, and I'm going to be adding them up. So I'm going to have these plus signs between them. So that is the dot product of u with itself. Now, this simplifies greatly because u1 times u1 is just u1 squared, and u2 times u2 is just u2 squared, on out to un times un is un squared. So we see that when I take the dot product of a vector with itself, I'm simply getting the sum of the squares of the components. And we will easily recognize that as the square of the length of the vector u. In other words, the length of the vector u squared can always be expressed as a dot product of the vector with itself. All right. Now this formula is incredibly useful because it allows us to take questions about length and turn them into questions about dot products. That's incredibly useful. But it also says that anytime I'm doing a calculation and I see the vector u dotted with itself, I can always feel free to reinterpret that as a length. I can think of that as the length of u squared. And we'll see that that's a very useful thing to know, right? That anytime I see a dot product of a vector with itself, it can always be interpreted as a length squared. Now let's take a look at some properties of the length function. And these properties, there's two of them embodied in theorem 1.3. So in this theorem, let v be a vector in Rn, and let c be a scalar. Let's take a look at this first property, property A. Property A says that the length of a vector is 0 if and only if v is the 0 vector. Now remember, there's two implications here, right? It says if we see that the length of a vector is 0, then that vector must be the 0 vector, and if we're looking at the 0 vector, then its length must be 0. All right, the second property says something interesting. It says, suppose that I scale a vector by c and then compute the length of that resulting scaled vector. This result says that that's the same as computing the length of the vector and then multiplying that by the absolute value of the scaling quantity. In other words, what this says is something like, if I take a vector and scale it by 2, then the length of that resulting vector is going to be 2 times the original length of that vector. All right, now we'll explore these. We'll look at proofs of these at the document camera, so join me over there. We'll look at proofs of properties A and B of theorem 1.3. All right, welcome to the document camera. Let's take a look at the proofs of parts A and B of theorem 1.3. And v is going to be a generic vector in Rn, and c is going to be a scalar. So let's just set up some components for v. Let's just say throughout this proof that v will have components v1, v2, on out to v sub n. And let's take look at this first part. Now remember, in A, there are two implications, right? We have to show that if the length of v is equal to 0, then v must be the 0 vector. And then we have to show the reverse implication, that if v is equal to 0, then the length of v must equal 0. So this is a two-way implication. That's what's implied by this if and only if. Now let's take a look at this direction, right? Let's assume that the length of v is 0. So we're going to suppose that the length of v is 0. Now where does that lead us to? Well, let's imagine, what is the length of v? It's the sum of the squares of the components, right? And so we know that when I take the square root of the sum of the squares of the components, that's equal to 0. Now what does that imply? Well, I can square both sides. I can equate this with, or this is equivalent to v1 squared plus v2 squared on out to vn squared equaling 0. Now here's the only subtle part of the argument, right? Each one of these vi squared, so v1 squared, v2 squared, up to vn squared, those are all numbers that are necessarily bigger than or equal to 0, okay? And to say that the sum of a bunch of numbers that are bigger than or equal to 0 is equal to 0 forces each and every one of these squares to equal 0. And that means that each one of the v sub i's, v1, v2, up through vn, must itself be equal to 0. Another way to think about this is if any one of these, let's say V1, if V1 were positive, then this V1 squared would already be positive, and by adding on a bunch of non-negative numbers, it would force this sum to be positive. So we know that all of these VI's, V1, V2, up through Vn, must be equal to 0. Okay, so let's just kind of write this out. So if this is true, I'm going to continue the argument up here. Then V1 squared is equal to 0. V2 squared is equal to 0. On out to V sub n squared is equal to 0. Well, the only way V1 squared can equal 0 is if V1 is equal to 0. So V1 has to equal 0. V2 has to equal 0. On out to Vn must equal 0. And that means that V is a vector, all of whose components are 0, and that's what we call the 0 vector. So we've shown this direction, that if the length of the vector is 0, it must coincide with the 0 vector, or it must imply that that's the 0 vector. The other direction is actually quite a bit simpler, because we know if we have the 0 vector, let me just make a little line of demarcation here. I'll just say this, on the other hand. If V is the 0 vector, then we know what? That V consists of a vector, all of whose components are 0. And the length of V is going to be the sum of 0 squared plus 0 squared. And out to 0 squared, that's our definition of length, and that's equal to 0. So we've shown this direction as well. So once again, we said if the length is 0, it must be the 0 vector. That was the first half of this argument. And then we showed that if the vector is 0, it is the 0 vector, it must have length 0. That's the easier half, but that's what we did here. All right, let's go to part B. So this is the proof of part A. Let's go to part B. This is a little more straightforward. You just kind of follow your nose. We want to take our vector V. We want to scale it by a factor of c. We want to compute the length, and then show that we can manipulate it. We can show that by working through some algebraic steps that we can equate that with the absolute value of c times the length of V. So this is kind of just a follow your nose proof. We just start here on the left hand side and we just kind of work our way to this right hand side. So let's take c and multiply it by this vector V. We know that that has the effect of changing all of these components by that factor of c. So we'll have CV1, CV2, out to CVN. Now what's the length of this vector? Well, it's going to be the sum of the squares of these components. Okay, and now we can apply the square. We can write this as c squared v1 squared, c squared v2 squared, c squared vn squared. And quite honestly, if you wanted to skip from here right to here, that would be fine. Now, we have a common c squared, right? Each and every one of the terms here has a c squared in it, so we can use factoring. We can pull the c squared out. Okay, now here comes the only subtle step in the whole proof, I think. If I want to pull this c squared through the square root, I have to understand that that value of c, it could be positive or it could be negative or it could be 0. But no matter what, when I pull it through this square root, it doesn't pull through as c. It comes out as the absolute value of c. So I'll have the absolute value of c here. And inside the radical, I'll have v1 squared, v2 squared, up through vn squared. And now I just have to recognize that this is exactly what we mean by the length of the vector v. Okay, and that brings a conclusion to our proof of Theorem 1.3 Part B, this fact about scaling and the way that scaling works with the length function. It's a nice result. It's very helpful from time to time just to be able to pull these scalars out and kind of isolate the length of v. So be ready to use that when needed. Okay, so I will head back to the class notes and continue. A vector u in Rn is called a unit vector, provided that it has length 1. That is, the length of u is equal to 1. Now, unit vectors play an important role in our study because we can think of them as pure direction vectors. In other words, their length is now a unit, and we can think of them as simply pointing in some direction. Now, in order to get comfortable with this idea of a unit vector and to get a glimpse of how they can be used, I want to work a couple of problems with you. So I've set up 2 problems here for us to study. We'll look at these problems in detail, and we'll look at their solutions under the document camera. So join me over there for a discussion of problems 1 and 2. All right, welcome back to the document camera. Let's take a look at this first problem. So let u be a non-zero vector in n-dimensional space, and we want to show that this process of multiplying the vector u by this reciprocal of the length of the vector always produces a unit vector. Now, how do we show that something's a unit vector? We have to show that its length is equal to 1. So the acid test for us here is going to be to compute the length of this vector and to show that it's equal to 1. So let's set out on this task. We've got to compute the length of a vector of this form. So this is asking for the length of this vector. Now, we have at our disposal Theorem 1.3 Part B, which tells us that anytime we're computing the length of a vector of the form a scalar times a vector, we can pull the scalar through as its absolute value. So we've got Theorem 1.3b that allows us to basically make this conclusion. We can pull the scalar through as its absolute value and then compute the length of the vector u itself. So we can simply do this product. Now, all we have to observe is that the length of the vector u is always a positive number for a non-zero vector. So this is already a positive number. So these absolute values are superfluous. We can simply rewrite this as 1 over the length of u times the length of u. And this product here is simply equal to 1. So this action of taking a vector and multiplying by the reciprocal of its length always produces a unit vector. All right, that's the result of problem 1. Now that's an important idea, right? So if I want to create a unit vector that points in exactly the same direction as the vector u, I can just divide by or multiply by the reciprocal of the length of that vector. All right, now let's put that to use here in problem 2. Right? We want to write this vector u as a pure magnitude, a scalar, times a pure direction vector. Well, the direction vector that we're going to pick is the one that I get by doing this action. I'm going to compute the length of u, and I'm going to multiply by the reciprocal of its length. That's going to give me the pure direction of u. And then I can simply multiply by the length of u to get the pure magnitude part. Let's take a look at this in action. So let's first get the length of the vector u. So the length of the vector u is what I get by taking the square root of the sum of the squares of the components. So I'm going to get a 9, a 16, and 144. Now I've set this one up to work out nicely. These three numbers together give me 169, which is a perfect square. That's 13 squared. So the length of this vector u is 13. Now what I'm going to do is use this result to create a unit vector. I can take this vector u, and when I multiply by 1 over 13, that's going to be a pure unit vector. Okay, so here's the idea. My vector u, I can write as 13 times 1/13 of the vector u. This part's going to be a pure unit vector by this result, and that's a pure length. That's the length of the vector. Now let me finish this up by rewriting this in terms of the components. So I'm multiplying by a 13th, so everything's going to get scaled by that same factor of a 13th. So I'll have 3/13. I'm going to have -4/13 and 12/13. Okay? This part is a pure unit vector by our first result. This vector has length 1, and this information here, the scalar in front, is the length of the vector. So I've now got my vector u expressed as a pure length or a pure magnitude times a pure direction. All right, I hope that helps. I've made a little note down here just so you can refer to this process. This process of turning a vector into a unit vector is called normalization. All right, so just we have a term for this process of taking a vector and normalizing it, turning it into a pure direction vector. All right, that's all I want to say about problems 1 and 2 here on this page. So let's head back to the course notes and continue. All right, I want to talk with you about standard unit vectors. In each space Rn, there is a set of standard unit vectors. So for example, when n is equal to 2, when we're in the plane, there are 2 standard unit vectors, and you should think of them as direction vectors that are pointing in the x direction, the positive x direction, and in the positive y direction. So we have a vector called E1, which has components 1 and 0, and a vector called E2, which has components 0 and 1. So E1 is pointing down the positive x-axis, if you will, and E2 is pointing down the positive y-axis. For n equals 3, we have 3 standard unit vectors named E1, E2, and E3. And E1 is of the form 1, 0, 0. E2 is of the form 0, 1, 0. And E3 is of the form 0, 0, 1. So hopefully you can see the pattern that's being set up here, right? The subscript of the vector E is telling you in which component there's a 1, and all of the other components are 0, right? So in both cases, in both E2s, we have a 1 in the second component, and all of the other components are 0. Now this pattern persists. So for example, when n equals 4, there are going to be 4 standard unit vectors, and E3, for example, will have a 3 in component 1, a 1 in component 3, and zeros everywhere else. So the important thing to take away from this is no matter which dimensional space you're in, there's going to be a set of standard unit vectors. All right, now what I want to do is show you, it's actually a very easy problem, but I want to show you a problem, work out a problem with you that says that any vector in Rn can be written as a linear combination of special unit vectors. So our special unit vectors allow us to quickly express any vector in Rn as a linear combination of the special unit vectors. So join me over at the document camera and we'll work out this problem in detail. So I want to show you this result, but I'm going to restrict myself to R3 just to kind of keep things tidy. Once you see the proof for R3, you'll be able to work this out in any dimension. So let's start with a vector V, a generic vector in R3. So it has components, let's say V1, V2, and V3. And remember, in R3, we have 3 standard unit vectors, and they would be typically labeled E1. Now E1 puts a 1 in the first component and has zeros everywhere else. E2 has a 1 in the second component and zeros elsewhere. And then E3 has a 1 in the third component and zeros elsewhere. Now what I want to show you, and this is not hard, but I want to show you that this vector v can be written as a linear combination of the vectors E1, E2, and E3. And the observation is this: if I take E1 and scale it by V1, we get V1 multiplying each of the components. So we're going to simply get V1, 0, 0. And if I take V2 and scale E2 by V2, we're going to get a 0, a V2, and a 0. And we're going to do likewise. We're going to multiply or scale the vector E3 by V3. All right. And now the last step is just to do some vector addition. If I add these three vectors together, so if I form V1, E1 plus V2, E2 plus V3, E3, if I add those vectors together, they're going to add component-wise. And so we can see the first component of the resultant is just going to be V1. The second component of the resultant is going to be V2. And the third component of the resultant will be V3. But the vector with components V1, V2, and V3 is just the original vector V. And so what this is showing us is that this vector V can simply be written as a linear combination of the standard unit vectors. And this would apply in any dimension, right? So if you're in n-dimensional space and you had a vector with components V1, V2, on up through Vn, so a vector of length n, you would have n standard unit vectors in this n-dimensional space, and you could easily generalize this result to say you take V1 times the unit vector E1, V2 times E2, and you would continue to pair up a component with its corresponding standard direction, and you'd have a result like this. And that's a helpful idea from time to time, to be able to think of a vector as a linear combination of some standard unit vectors. Okay, let's head back to the class notes. Now our next result is one of the most celebrated results in mathematics, and you'll see it showing up in lots of different math courses that you could take. For the vector form of the Cauchy-Schwarz inequality looks like this. It says, for all vectors u and v in n-dimensional space, the dot product of u and v in absolute value cannot be bigger than, in other words, it'll always be less than or equal to, the product of the lengths of the two vectors. So what the Cauchy-Schwarz inequality does is it says u dot v is going to be bounded, right? It's going to be in absolute value no bigger than the product of the lengths of the vector. So it puts bounds on the size of the dot product. So here's an example. So suppose I told you that u is a vector with length 2 and v is a vector with length 5. What the Cauchy-Schwarz inequality is going to tell us is that the value of u dot 5 has to land somewhere between -10 and 10. That's what it would mean to say that its absolute value is bounded by 2 times 5. That means u dot v could be positive, it could be negative, but it has to sit between -10 and 10. So it gives us bounds on the size of the dot product of the two vectors u and v. Now, in order to get comfortable with this Cauchy-Schwarz inequality, let's work a couple of problems. We'll go to the document camera and work out these two problems to gain some level of comfort with the Cauchy-Schwarz inequality. So join me over at the document camera to investigate these two problems. All right, welcome to the document camera. What we want to do is verify the result of the Cauchy-Schwarz inequality for this pair of vectors in R3. So let's just remind ourselves what we're trying to show. The Cauchy-Schwarz inequality says that u dot v in absolute value will be less than or equal to the length of u times the length of v. So what we're going to do is just compute these three quantities. We'll compute u dot v, we'll compute the length of u and the length of v, and we'll just compare and see if this inequality is satisfied. All right, let's work on u dot v first. So when we compute u dot v, what we're thinking of is component-wise multiplication. So we'll have the 1 times the 3. We'll have the 2 times the 1. And then we'll have -1 times -4. And then these products are added together. So the u dot v will be a 3 plus a 2 plus a 4, which is 9. So u dot v, in absolute value, it'll be 9 because it's already positive. All right, now let's compute the length of u and the length of v. So the length of u is going to be the sum of the squares of its components with a square root wrapped around that. So we're going to have a 1 squared or a 1, a 4, and a 1. And that's going to be the square root of 6. And the length of v is going to be a 9, a 1, and a 16, which will give us the square root of 26. Now, when we take the product of the lengths of u and the lengths of v, that's going to be the square root of 6 times the square root of 26. And when you carry out that calculation, you get a number on the order of, so this is not exactly equal to, but it's approximately equal to 12.5. So when we compare our two sides, we can see that the Cauchy-Schwarz inequality, we can verify it, right? This left-hand side is 9, and this right-hand side is on the order of 12.5. So we can verify the result of the Cauchy-Schwarz inequality in this case. All right, let's take a look at the second problem. Let u and v be vectors in n-dimensional space. If the length of u is 3 and the length of v is 6, then what are the largest and smallest possible values for u dot v? Well, the Cauchy-Schwarz inequality puts a bound on the size of u dot v, right? It says in absolute value, u dot v cannot be bigger than the length of u times the length of v. So it can't be any bigger than 3 times 6 or 18. So if this is the absolute value of u dot v, that says that u dot v itself would be between 18 and -18. So we can see that the absolute value, the u dot v itself will land between these two numbers. That means that the smallest possible value for u dot v would be -18, and the largest possible value for u dot v would be 18. Okay, let's head back to the class slides, and we'll continue this discussion. Now I'm calling our next result a child of the Cauchy-Schwarz inequality because it can be proved directly from the Cauchy-Schwarz inequality. So it'll be an easy consequence of Cauchy-Schwarz. But this result has got a name of its own, and it's a celebrated result in its own right, and it's called the triangle inequality. And it says the following. It says, for all vectors u and v in n-dimensional space, the length of the sum of u and v is bounded by the sum of the lengths of u and v. And the geometric meaning of this is actually quite simple. We know that anytime I have a pair of vectors u and v, that there's an implied triangle, u, v, and u plus v, and I've got that triangle drawn up here. So we've got this implied triangle. And we also know that for a triangle, that if I take any one of its sides, so the length of any one of its sides is bounded above by the sum of the lengths of the other two sides. So this triangle inequality is just applying it to this particular side. It says this side, u plus v, its length is bounded above by the sum of the lengths of the other two sides. So this is why this result, this very important result, is called the triangle inequality, because we can see it in this implied triangle u, v, and u plus v. Now I want to show you a quick proof of the triangle inequality because it brings together so many of the things that we've been working on. So we'll see that it's a very elegant proof and it uses a lot of the material that we've been studying in this section so far. Now remember, we're trying to correlate the length of u plus v with the lengths of u and the lengths of v and form an inequality. Let's start with the length of u plus v. And the thing to do, the thing that cracks this open is we don't want to consider just the length of u plus v. We want to consider the length of u plus v squared. And now the thing that really helps us here is, if you remember, we can always calculate the length of a vector squared by thinking of it as the dot product of the vector with itself. Okay, so we can think of the length of u plus v squared as u plus v dotted with u plus v. And now we can use our distributive law. We can FOIL this, so to speak, right? We'll have u dot u. We'll have u dot v. We'll have v dot u. And we'll have v dot v. Now, let's recognize what's going on here. Anytime I see a dot product of a vector with itself, when I see u dot u, I know that another way of thinking about that is as the length of u squared. So I can replace this one by length of u squared. Now here I can use the commutative law and think of v dot u as just u dot v. So this is 2 u dot v. And here I can think of this as the length of v squared. Now here's where the Cauchy-Schwarz inequality comes in. This u dot v, I can replace u dot v. Let me just write it off to the side here. The Cauchy-Schwarz inequality says that u dot v will never be bigger than the length of u times the length of v. That's the Cauchy-Schwarz inequality. So it allows me to replace this by the bigger term, length of u times the length of v, which will introduce an inequality here. Okay? And now here's the last magic part. When I see this term here, if I stare at this, I'll recognize that this is just a perfect square. This is just the square of the length of u plus the length of v. Okay? Now this last step, we just have to be a little bit careful here. I've got this term here, u plus v squared, length of u plus v squared, is less than the length of u plus the length of v squared. Now, the length of u plus v is a positive number, or at least a non-negative number, and the length of u plus the length of v is also a non-negative number. So I can take the square roots here, and I have to understand that there's an inequality here, but when I take the square roots, I can compare them as the length of u plus v is less than or equal to the length of u plus the length of v. And that's our triangle inequality. This is the result we were headed for. So this shows you how we can easily get the triangle inequality essentially from the Cauchy-Schwarz inequality. That's what kind of breaks this open. But remember, the master step at the beginning was to compute the length of u plus v squared using the fact that I can just compute it using the dot product of the vector with itself. All right, and then I would use my distributive laws and the Cauchy-Schwarz inequality to help me along the way. Anyways, it's a beautiful result, a very nice proof, and hopefully you have a nice appreciation for this triangle inequality and how we can prove it. Let's head back to the class notes. So now I want to talk about how to measure the distance between a pair of vectors. And our definition of the distance between a pair of vectors is motivated by this picture. So if I have a vector u and a vector v, and I want to talk about the distance between the vectors, I'm really thinking about computing the distance between the tips of the vectors. And an easy way to think about how we can calculate that distance is to think about the vector v minus u. So think about the vector that runs from the tip of u to the tip of v. That's the vector v minus u. So what we're going to say is the distance from u to v is simply the length of v minus u. So let's read it together down here. So let u and v be vectors in n-dimensional space. The distance from u to v, denoted by this symbol duv, the distance from u to v, is the length of the vector v minus u. In other words, the distance from u to v is simply the length of u minus v. Now what I want to do to help us strengthen this idea of distance is to work a couple of problems. In the first problem, we're just computing the distance between a pair of vectors. And in the second problem, we're convincing ourselves that whether we talk about the distance from u to v or the distance from v to u, we get the same thing. In other words, we really shouldn't think of the distance as depending upon the order in which we feed them into this function. So the distance from u to v and the distance from v to u will always compute to the same thing. So join me over at the document camera to work out these problems. All right, welcome back to the document camera. Let's work out these problems. The first problem is asking us to compute the distance between a vector u and a vector v. The first step is going to be to calculate v minus u, to get the vector v minus u. So let's rewrite these vectors. I find this helpful at times, just to rewrite the vector v and the vector u. We can stack them. It helps us kind of think our way through this a little bit. So when I'm computing v minus u, I'm doing component-wise subtraction. 1 minus 1 is 0. 2 minus 5 is negative 3. Negative 2 minus negative 2 is 0. And 1 minus a minus 3 is going to be 4. So that's our vector v minus u. That's the first step into computing the distance between these two vectors. The next step is to get the length of v minus u. So the distance from u to v is going to be the length of the vector v minus u, which we've already computed. And so now we just have to take the square root of the sum of the squares of the components. So 0 squared is 0. Negative 3 squared is 9. 0 squared is 0. And 4 squared is 16. And I've cooked this one up to work out nicely. 9 and 16 are 25. And so that means that the distance between these vectors is 5. There's 5 units of distance between them. And that is the conclusion to this first problem. Now, let's take a look at the second problem. I want to let u and v be vectors in Rn. I want to show that the distance from u to v is the same as the distance from v to u. So in other words, we read this as if the order matters. We say that this is the distance from u to v, and we would say this is the distance from v to u. And the point of this problem is to say it really doesn't matter if we talk about it as the distance from u to v or the distance from v to u. We can just talk about the distance between the vectors. It's coherent either way. Now, let's just remember that we've expressed this as the length of v minus u. So when we talk about the distance from u to v, we're really thinking about it as the length of v minus u. Now, all we have to do is just a little trick here. We just have to understand that v minus u, let me show you a little side calculation here. When I take negative 1, the scalar negative 1 times u minus v, I can distribute that and I get negative 1 times u plus v, and I can commute the order of the vector addition. And I realize that that's just the same thing as v minus u. So what this is telling me is anytime I see the vector v minus u, I'm free to replace it with negative 1 times u minus v. So I can make a free replacement. I can replace this by this. They're the same thing. So let's see how that helps us here. right? In place of v minus u, I'm going to write this. Now, one of my properties of length said that I can write this as the absolute value of the scalar times the length of the vector, in this case, u minus v. Okay, but the absolute value of -1 is simply 1, so that drops out. And I'm just left with the length of u minus v. And we could read that as the distance from v to u, okay? The distance from v to u would be the length of u minus v. The distance from u to v would be the length of v minus u, but it turns out that no matter how you work this out, you're going to get the same result. So we can really speak of just the distance between v and u, or the distance from u to v, or the distance from v to u, and those would all be the same thing. They all coincide. Okay, so hopefully that gives you some insight into how to compute a distance and how to think about the distance between a pair of. All right, I want to give you the proof of the Cauchy-Schwarz inequality. As you'll see, it's a little subtle, but it does use all of the elements that we've been working on, so it's kind of a nice thing to look at this point. I'm not going to ask you to reproduce this, but I think it would be nice just to show you how everything we've been working on is brought to bear on this proof. Now, let's take a look at the statement, right? We're trying to show that u dot v, that dot product in absolute value is bounded by the product of the lengths of u and v. That's the Cauchy-Schwarz inequality. All right, now it begins, I would say this is the first phase of the argument, right? Phase 1 is to realize that the object that you want to study is this. And I'm going to let x just be any real scalar. All right, so the insight is that this is the object that you want to study, is the dot product between these kind of special linear combinations of u and v. So I'm letting x just stand for an indeterminate, an unknown, right? It's just going to be some scalar x times u plus v, that same scalar x times u plus v, and I'm taking the dot product of these two. Now we know from our expansion formula that we can work this out, and we're going to get the product of these first terms, so that's going to give me an x squared u dot u. I'm going to get these last terms. That's going to give me an x u dot v. I'm going to get these inner terms, and that's going to give me an x v dot u, but I'll write that as x u dot v. And then I'll get the last terms, v dot v. Okay, so I've got all these terms. Now, let's do a couple of things. When I see u dot u and I see v dot v, I can think of those as the lengths of u and v squared. So this is now of the form length of u squared times x squared. I can combine these two terms to give me a 2 u dot v x, and I can think of this as the length of v squared. All right. Now I'm temporarily going to change up my notation here just to kind of make this look a little more tractable, right? I'm going to identify this number. I'm going to call that A. And I'm going to call this number B. And I'm going to call this number C. And what we're seeing is that when I take these linear combinations and take their dot products, that they give us something of the form ax squared plus bx plus c. All right? So I'm going to call this p of x. So the result of this dot product is a quadratic polynomial. All right, so that's like the first big insight here, right? That when I take these linear combinations and I leave x as kind of this scalar that I can set freely, that gives me a quadratic expression in that scalar x, and that these coefficients a, b, and c are all expressed in terms of lengths of u, lengths of v, and dot products of u and v. So it's very insightful, and that's kind of what cracks this open, is that this is a quadratic function of that scalar x. Now the other thing we notice is that this coefficient a, since it's a length, right, and we're assuming that u is not a trivial vector, right? Let's just assume that u is something other than the zero vector, that this is going to be a positive coefficient here. This a is a positive number. So in fact, we have a quadratic expression. The graph of this is going to open upwards, right? And the other observation that we want to make, right, is that since this is a dot product of a vector with itself, this function p of x is always going to be bigger than or equal to 0. So let's write, this is kind of phase 2 of the argument. Let's just make some observations, right? That the coefficient a is positive and p of x is bigger than or equal to 0 because it's a dot product of a vector with itself. Okay, now geometrically, what does that tell us? It says we have a quadratic function. It's always bigger than or equal to 0, and its leading coefficient is positive. So if I think about what the graph of this function has to look like, it really breaks down into two cases, right? Right. Case 1 is that this function, this quadratic function, is always strictly positive. In other words, it just lives its entire life in this upper half plane. It never crosses the x-axis. So we would say that this is the case where there are no roots. Right? The other case is a little more subtle. We know it's still opening upwards. It's a quadratic that's opening upwards, but it could equal 0 at some point. But if it does equal 0, it's just coming down. It's kissing the x-axis and moving back up. And this is the case where we have one real root, okay? But the idea is if it had two real roots, if it had two places where it touched the x-axis, at some point the quadratic would have to be negative, and that would violate this basic property. So it's a quadratic that's opening upwards. It's bigger than or equal to 0 everywhere, so it either has no roots or it has at most one real root, but we know that it can't have two real roots, okay? Now let's go to phase 3 of the argument. Let's leverage this and go into phase 3. We know how to talk about the roots of a quadratic function, right? We know that the roots are going to be of the form negative b plus or minus b squared minus 4ac all divided by 2a. And the important object in understanding the root structure of a quadratic function is this part here, b squared minus 4ac. This part's called the discriminant, and it basically tells you when you have no roots, one root, or two roots. All right? So if b squared minus 4ac is negative, if this quantity is negative, then this expression here would correspond to two complex roots and no real roots. So this case here corresponds to b squared minus 4ac being negative. If b squared minus 4ac is equal to 0, so in other words, if this somehow magically combines to give us equal to 0, then this plus or minus term drops out, right? We can just effectively drop that out, and we can see we only have one real root, and it's going to be at negative b over 2a. So the plus minus part just drops out. It's equal to 0. So this corresponds to b squared minus 4ac equaling 0. And the case where b squared minus 4ac is strictly positive would correspond to having two real roots, one with the plus sign and one with the negative sign. And that's not happening in this case. So let's go through the argument just to make sure we're keeping this all together, right? When I form this inner product, I get a quadratic function, a quadratic polynomial, The leading coefficient is positive. The polynomial is always bigger than or equal to 0. And as a result, we know that b squared minus 4ac is either negative or at most 0. So the consequence of this analysis is that b squared minus 4ac is always going to have to be less than or equal to 0. It's either this case or this case. So we can combine those to say that b squared minus 4ac is less than or equal to 0. Now let's go back and rephrase this in terms of a, b, and c. And let me just do one next step. I'm going to write b squared is less than or equal to 4ac. All right, so in phase 4, and this is the final phase of the argument, we're just going to bring these quantities back into this expression. So b squared is going to be 4 times u dot v squared. And this is less than or equal to 4 times a times c. Okay, now take square roots. We'll cancel the 4 and take square roots of both sides. Okay, now we know what to do on this side. The length of u is always a positive, well, a number that's bigger than or equal to 0, and the length of v is a number that's bigger than or equal to 0. So this extreme right-hand side here just boils down to the length of u times the length of v. No absolute values are necessary. On this side, we have to be a little bit careful because we know that u dot v could be positive or it could be negative. So when we look at the square root of its square, we have to be careful to interpret this as the absolute value of u dot v. And so this is the Cauchy-Schwarz inequality. It tells us that the absolute value of u dot v is always bounded above by the length of u times the length of v. So this is the celebrated and wonderful Cauchy-Schwarz inequality. Now, as you can see, this is really subtle, right? You'd be hard-pressed to work out this proof without some kind of extreme inspiration. So we're standing on the shoulders of giants here when we see this proof worked out. Nonetheless, this is a foundational result. This is the beginning of a lot of interesting work, geometrical work in these vector spaces. So we have the Cauchy-Schwarz inequality. I wanted you to see how the proof looks. I'm not going to hold you to this, but I thought you might enjoy seeing this in some detail.